Okay, so we're on topic 4 now. So I guess I'm walking around today. Let's do a quick verbal recap of some of the skills and ideas that hopefully you guys remember from the last couple of days. Okay, one of the topics you guys need to know is basically safety with electricity. Okay, things like why do we have that third plug on the on electrical outlets, right? The idea of grounding electricity. Because if electricity goes through, whoa, this is weird me standing here now. I'm gonna get used to this. If electricity goes through a person, you get electrocuted, right? That third prong is meant to try to save you and protect you. I even had a test question about why there was like a chain running behind a truck. You guys remember seeing that one on the quiz yesterday? Right? And it's kind of the same idea, is that we want to ground electrons for safety purposes. Right? Another one of the things we would have talked about is ways we can measure electricity. And there are two. One is amps, amperes, same thing, which is current. And current is really about how many electrons are moving. And so the analogy I love to give is if you have kids walking down the hallway, if you have 4 kids versus 400, well, 400 is more current. And there were some test questions yesterday on your quiz. Let's see, one of them was about like a waterfall, I think. If you guys remember that one. Another one was about like some sort of bucket that had a little spout on it. Right? And if there's more water pouring, then you have more current. Okay. The other way that you can measure electricity is a voltage. And voltage is all about how much energy it has. So if I were to drop a whole bunch of pencils from this high or from this high, like one is a foot off the ground, one is 10 feet off the ground, hopefully you guys would agree that if you drop something further, it's going to pick up more speed. Right? So the analogy there would be if you had kids running down the hallway versus walking down the hallway. That's like the push that gets them going, the oomph that gets going, right? So that's another thing we've talked about. We also talked about static electricity versus current. And why don't I start my lesson with these slides here now? Static electricity is if you do like rub your feet against the floor and then go zap somebody once, right? Static electricity happens like when your clothes washing machine, like the dryer, right? Spins around and around in a circle, and it kind of builds up some static cling, and like you can almost like have to like tear your clothes apart a little bit. It gives a little bit of like a zzzt, you know what I'm talking about there? How'd that happen? Right. And I tried to show you guys some static electricity with some of our demos. Today we're going to very specifically talk about circuits. And today we're going to talk about circuits, the idea about how to actually build a circuit that will actually provide electricity very purposefully. And the one very logical field of study that comes out of this would be an electrician. Right? An electrician, someone who goes into a house, right, and puts in all the wiring, puts in the lights, puts in the light switches, right? They would really want to care about circuits. Does that make sense? So that's kind of today's goal. And by no means am I an expert, by the way. So if anyone here has like a mom or dad who like works as an electrician, you could probably ask them, and they know way more about this than I do. But our goal today is to talk about basic circuits, hence the topic. Sound good? So, first thing I want to remind you guys then is, what is electricity? Well, it's when electrons flow around a circuit in a continuous direction. And if they keep going in the same direction, do you guys remember what name that was given? Direct current, yeah, DC, direct current. Direct current. Where it just keeps going in the same direction over and over and over again. And most things that we'll use in like basic circuits will actually be through direct current. There's actually a major flaw with direct current though, okay? And really, it's basically this pushing theory, is that this electron right here pushes this one, which pushes this one, which pushes this one, which pushes this one, and it's basically one big long train of everybody basically flowing in a circle. There is a problem with this, however. If you need to build a very, very, very big circuit, and you have to push electrons over a long distance, direct current eventually gets a little bit tired, because you always have to have one pushing the next, pushing the next. Do you guys recall a slide I had a few lessons ago with a big power line with transformers? Imagine that you got like those big, can we even see them from out here? I don't know, like those big electrical lines that you might see running along the sides of the road, maybe along the sides of the highway. You guys ever seen those before? Right? And you got to move electricity from Lethbridge to Coaldale. right? And so you got big power lines going there. Direct current actually has a bit of an issue then, because if you're always pushing and pushing and pushing, you need to have high voltage. Yeah, good call. It was 500,000 volts to try to push all these electrons a long distance, right? The further you have to try to push these things, the more challenging it becomes, right? So we've actually discovered a second way of moving electricity. And this one isn't something I've assessed you on yet, although it was one of the answers on the test. Hopefully you didn't pick it. But there's a second way of doing current. It's known as AC current. Anybody ever heard of AC current before? Anyone know what the A stands for? Alternating. Yeah, nice. Alternating. So I may as well talk about that right now before I go a little bit too far here. Alternating current is basically where you set up a system where electrons go this way and then back, and then this way and then back. And you keep sending them back and forth and back and forth. And what's nice about alternating current is that rather than it continually having to keep giving a big push, big push, big push to keep moving these electrons, especially big distances, what ends up happening is the necessary electrons, the ones that you really need, the ones that are going to go through this lamp, or we have a better name for it, we call it a load. Well, rather than constantly sending electrons through the load in one direction, we actually can send them this way, and then those same electrons go back this way, and then those same electrons go back this way again. And so it might be the same 7 electrons that are constantly going back and forth through the light bulb. So rather than it having to be this electron that goes through the light bulb, then this one goes through, then this one goes through, then this one goes through. See how like in direct current? Ooh, we better move that blind, don't we? How in direct current, it's going to cause every single electron will eventually go through that section there. In alternating current, it's the same few electrons just going basically back and forth. Ryan, how's that? Is that out of your face yet? Not yet. Now it's better, but I broke it. This one too. I always want to have sunlight in the classroom, and then of course it. Good. Okay. Anybody else? Oh, no, this one too. This one here still? Still more, huh? We're good now? Okay. I know, now there's no light anymore. Okay, where was I? Do you guys get the idea then of alternating current? Where basically the idea is if you can, you push it this way and this way, back and forth, back and forth. Okay. In our household voltage, we actually use about 110 to 120 volts of alternating current. And so if you were to draw a picture here, this circuit is actually not all just going in one direction, it's back and forth. Okay, let's move on to my notes here. You guys should already hopefully know some of the terminology I've got on the slide here. In order for you to basically run any sort of circuit, you need to have 3 things at the very least. You have to have a battery or a power source. You have to have something that pushes the electrons. You have to have something that's like running, right? What's the point of the electricity? Is it to make sound or motion or light or heat? So the word we use is the word load. And then you're going to want to have some sort of wires. If you don't have some sort of wires, how are the electrons going to move? But there's also one more thing we often put into a circuit, a switch. And doesn't that make sense though? Because if you don't have a switch in a circuit, then the current is always on, right? I mean, try to find me a device that doesn't have a switch. Our lights turn on and off. My little board here has a switch that turns on and off. Your cell phones have an on and off button, right? As much as, like Apple, I think, was really clever. Like when they first made their iPhones, they literally put 2 buttons on it, maybe 4, I guess. Up sound and down sound. Off, and then the home screen button, right? But you still had to have at least some sort of button to turn things on and off, right? So what I've got here is a couple of diagrams that are trying to explain basically how a switch might work. So let's actually start with the one further over here on the right. If you guys can see this circuit right here, there's actually 2 circuits. Right here, you've got a battery, right? And the electrons are going to run through the battery, so why don't we have them go this way? They're going to run through the battery like this, through like this. This switch is closed, so they can keep going like this. They can go through the light bulb, back around and into the battery again. Look, I have a full circuit. That light bulb's on. But let's use another color. I'll use red now. Electrons go this way, they go this way, they go through the switch, they go through this wire, but then they had a choice right here. They could have gone through the light bulb. I'm going to have them go back through the second switch. And they would love to go through the switch right here, but say there's a bit of a gap there. By lifting this little piece of metal up, well, all of a sudden now the switch is not working. And so the electrons would like to keep going this way here, but they can't because right here, there's a gap. See this? What was that? What's that? Okay, here's another example of a switch that maybe works on a bit of a different principle, but this is worth looking at as well. This is a doorbell, just a basic doorbell. Right? And what actually ends up happening in some switches is that they're always set in a permanently off position until you do something to move them to an on position. Okay, so look, here is a wire coming in right there, and here is a wire coming in right here. Okay, and this little piece right here, the one that I'm drawing in red, it's meant to be the last connection. So electrons are supposed to come in here. They're supposed to go back through here. And can you guys see how there's just a little bitty gap right there where I drew that? So therefore, there's no circuit. But when someone presses in on the doorknob, or not on the doorknob, on the doorbell, right? Press in on the doorbell, what ends up happening is this little flexible piece of metal right here, it gets pressed in, and all of a sudden this little gap is now missing, and now, hey, all of a sudden now there is a full circuit right here, and now the electrons can run through the circuit, and now the doorbell goes ding dong, or whatever your doorbell does, right? So there are two types of switches. So if I can recap what we've talked about here, this is a switch right here where it's always meant to be off, and by pressing in on it, that actually turns it on just temporarily. Whereas this is a switch right here, these two switches right here, where this switch right here is always meant to be on, but when you lift it up, then it kind of turns it off for a little bit, right? Those are your switches. Okay. Now I want to review a little bit of terminology in terms of how a battery works specifically. There are a couple of words that you guys need to know. If you're not familiar with these words, we got to memorize them. The words are anode and cathode. An anode is negative, yeah. And there was a silly way that I had to remember anode and cathode. It's that cats have paws. It's dumb, but boy, it works, doesn't it? So there's always two sides to a battery, right? Grab any battery, and there should always be the positive and negative side. Well, what does that mean? Well, it means that on the positive side, there's a whole bunch of pluses, and on the negative side, there's a whole bunch of negatives. And if I were to draw some sort of circuit around this battery, it definitely has to loop back on itself. I need for you guys to be able to tell me which way the electrons are moving. Which way do electrons want to move? Should I draw an arrow towards the negative? Or should I draw an arrow towards the positive? Which way are they going to move? Let's talk those through, because I heard someone actually say one of each next to me here. So let me draw this out nicely here just to make sure it's clear what I'm asking you. You could either have electrons go this way, according to the green arrows I'm drawing, or we could have electrons go this way according to the black arrows I draw. Only one of the two answers is correct. So take a second, think about it a bit more. Which way do you think the electrons are moving? Green arrows or black arrows? I heard both. All right, I'll tell you the right answer now. The answer is green. Let's talk about why. Now, there's actually a really confusing part to this. If you get to physics 30, we talk about conventional current, and it's one of the, yeah, Zainab's giving me like a, oh, stupid conventional current. But technically, electrons always go from negative to positive, and here's why. All these negatives right here, do they want to be by other negatives? Do negatives like being by other negatives? Well, no. Like charges repel. So this electron right here wants to get away. Now, it would love to go this way, but it can't because there's a barrier between them. It physically can't. So an electron will start to go this way. It wants to get away from other negatives. But one more thing. Where do negatives want to go towards? They want to go towards positive things, right? Because don't negatives and positives want to attract each other? Okay. Now, here's a really good question. Why don't these positive things right here, why don't they move? Where are positives found in atoms? Gabby? In the nucleus, yeah. And so therefore they can't move. Now, that's actually a reason why we'll eventually talk about something called conventional current. Way back in the 1800s, when Ben Franklin was first doing experiments, he actually thought it was the positives that moved. And because he didn't know positive from negative, he actually drew diagrams where he thought electrons were going from positive to negative. And sometimes we still work with those diagram drawings, but we call it conventional current. And basically the idea is this is the way things would, I'm using finger quotes here, would move if positives could move, but they can't. So it's actually the negatives that move. So I need you guys to know these words right here again. We've discussed this before. The word hot wire and neutral wire. Okay. The hot wire then is the ones that are going to the load. Okay. And so in this little diagram I've drawn up top here, I actually haven't drawn any load in there. So kind of in the middle here, why don't I just draw like a box? And I don't care what it is. It's a light bulb, it's a fan, it's a speaker. I'll call this the load. It means you always have to have two wires. You have to have the hot wire on this side, the one that is going from the negative source and it is going to your load. And then the other wire has to finish off the circuit, and this is known as the neutral wire. And so if you ever do any or even just see your parents doing any home electrician work, there's always supposed to be at least these two wires, a hot and a neutral wire. And preferably there's also a third wire. What would the third wire? The ground wire, yeah. So there should at least be that many. And sometimes it's even more complicated than that, but that's your bare minimum. So did I do a good job of explaining the concept of hot and neutral wires and how to identify them? Because that's something I'm going to need you to be able to do. Okay, so the hot wire is always coming from the negative side of a battery into the positive, yeah. So you just have to make sure you have your directions right. Okay. So here I've got another picture to help kind of illustrate the concepts I want to go for. I'm going to change this window too, I think. So sometimes when we draw batteries, we draw them looking like this. We draw this little shorthand convention. It's a long line and a short line. And the long line and short line is basically a shorthand way of saying this is a battery. Okay. Now here's how I remember which side is which. The little line is the minus sign, which means the big line has to be the positive side. So that's what this battery right here means. And this actually isn't one battery. Yeah. Because there's two batteries, right? But have you guys ever used a device where it says you need to put two batteries in it or four, right? For example, I've got those Wiimote controllers for playing the Wii, right? It requires two batteries, right? So that's actually what this convention is showing you here is there's actually two batteries here set up side by side. So now that we know that the big side is the positive and this is the negative side, it actually makes sense why the electrons are going this way right here. So just to recap one more time, if I were to ask you to tell me which one the hot wire is, I'll label two of them. This is wire 1 and this is wire 2. The hot wire is number 2, yeah, because it's the one that is receiving the source of electrons. It's going to the load, and then the neutral wire is going back to start. Right? And then here, hey, come on in. In this example right here, though, you guys can see how this thing right here is open. What do you think this symbol right here represents? Yeah, a switch, yeah. So this thing represents a light bulb, a load. This represents two batteries, two cells. This thing here represents a switch, and then just a basic line represents a wire. And so one of the tasks I need you guys to be ready for is known as being able to look at a wiring diagram and basically being able to interpret what's going on. This is almost guaranteed to be on your PAT, where they're going to give you a picture that looks like any of these ones right here, and you got to figure out what is happening. Right? And in general, with just a little bit of background information and a little common sense, hopefully you can look at it and try to identify, okay, here's what's going on. These are diagrams, by the way, for those light switches where, anybody have these in your house where you can go to one light switch and hit it and it turns the light off? And then you walk across the room and you go hit the other light switch and it turns it back on again? You ever have a fight with your brother or sister where they go like, I want it off, no, I want it on, right? And you keep clicking the two different light switches back and forth? Ever done that before? No. Here, by the way, is another thing I need you guys to know about. It's called either a variable resistor or a rheostat is the more common word. And you must have seen these before. These are more commonly known as a dimmer switch. You ever seen one of these little circular things that you twist and it makes the lights go down? Or maybe there's a little slider Have one of those. Yeah. Now, light bulbs aren't the only things, by the way, that have a variable resistor. There was a question on our test the other day, our quiz, that asked you about a drill at some point, and it asked you where you attach the drill bit. Okay. I don't actually want to talk about that question, but I want you to think about a drill. What if a drill had, like, say, a 7-speed drill? Well, each one of those speeds means that you kind of have a dimmer switch on your drill because it spins this fast, and it spins faster, and it spins faster, right? Well, okay, that also works too. Yeah, that's also a variable resistor. So if there's ever a device that has, like, different speeds, or how about this, different sounds, right? My speakers over there by the computer have a little volume knob. That's a variable resistor because it's changing how much current and voltage gets to the supply, making it thereby louder or smaller. Okay. Let's talk about these switches right here. These are those multiple switches. Let's see if we can kind of explain why they work. Do you see how there's two switches right here? There's one switch right here and one switch right here. And currently, it's in the off position because here's the way it works. The electricity wants to come from the negative, go through the hot wire to the light bulb, go through here. It's going to take the upwards route through the blue wire, and then right here, it gets stuck. Yeah, but here's the thing. You could turn on this switch right here, right? So imagine that in this diagram over here, you flicked switch 1. If you flick switch 1 into the other position, well, now all of a sudden, now there's a full circuit. So switch 1 could have worked. Or if you didn't flick switch 1, so imagine that you didn't flick on switch 1, it's still in the down position, but you flicked switch 2 instead, switch 2 would now go down, and that would be this diagram now here. And now, yeah, now it still works, right? But what if you toggled both switches? What if you turned on switch 1 and flipped it from down to up? And you flipped switch 2 and flipped it from up to down? Well, that would actually turn the light switch back off again. This is the mechanism then through which electricians can make it so that you have, like, what's known as a two-way switch. And there's even ways of having 3-way switches and 4-way switches where, like, any one of the light switches can actually turn something on or off, which is kind of cool. I want to skip ahead. No, I don't want to skip ahead. Never mind. Here's the slide I want to go to. This is a slide then that kind of talks about all the different things that you could put into, like, a diagram of a circuit. Right? For example, here's a really basic one at the top here. Down here you've got an electrical source, but we've already talked about this. What does this really mean if you see two of these guys right here? You have two batteries, yeah, right? Over here you have a conducting wire. Here you have a load, which looks like it's a light bulb, and here you have a switch. What I've got on this slide right here is a whole bunch of different things that you could put into a circuit if you wanted to. So if you guys can see here, I wonder whether I can zoom in a little bit. Is there a zoom function? There we go. Here we go. Now I got a zoom function. Let's zoom in on this. So if you ever see just a straight, like, line, it means it's a wire. And if you ever see a single one of these things where there's, like, a long line and a little line, that's one cell, one battery. But normally you don't just have one battery. Normally you have, like, say 2 or 3 or 4. Okay? Here's the picture for a lamp. It's maybe a little too blurry now, but basically it's a circle with, like, a little, like, curvy thing kind of in the middle. That's a lamp. This thing right here is a resistor. Okay? What does a resistor do? Well, it changes how much electricity you get by either slowing it down. Well, no, not only. Like, the one thing it does is it slows it down. I want to skip down here. This guy down here, though, is called a variable resistor. Can you guys see how it's the same little squiggly pattern? But there's a little line that comes out of it. A variable resistor means you can change how much resistance there is. So right now, these lights have really no resistance. They are on full blast. But if we had a dimmer switch, we could turn it down a little bit, turn it down a little bit, turn it down a little bit. But hang on. If I'm turning down the lights, what am I doing to the resistance? Making it higher, right? Because if there's more resistance, it then prevents your current from going through, right? So whenever you're actually turning on a dimmer switch and making something smaller, you're actually reducing. Sorry, when you make it smaller, you're increasing the resistance. What if I were to take my phone, right? And if I were to, on the side, I have my volume buttons, right? If I were to turn the volume up on my phone, what am I doing to the resistance if I'm turning the volume up? I'm decreasing the resistance, right? So it really has a backwards relationship. Okay. Here's a picture for a switch. Where's my... Oh, it's turned off again. Here's a picture for a switch, which is pretty basic. It's a couple of dots with a little line that's turned off. If we ever use one, and you either have an ammeter or a voltmeter, we typically put a circle with either the letter A or V inside of it. This one's an interesting one. This right here is known as a motor, because sometimes you have like a motor running, say, a fan of some type, right? A blender would use a motor. And then here's the last one I need you to know. It's called the fuse. What do fuses do again? They melt if they get too right. And the idea is this fuse right here, you can even see it. It melts if the current gets too high because they're trying to protect against electrical fires. Okay. So with that being said, I'm going to finish off my lesson because we actually are almost done. I just want to go back to the beginning here. I skipped this slide right here. Let me go back to this slide right here. This slide then talks more about resistors. Resistors are those devices that prevent, guys, stay with me, I'm almost done, that prevent the flow of current. And so, like we just said, if you turn up a resistor, it makes it softer or dimmer or slower, right? But if you turn down the resistance, now it's louder or brighter or faster. And so there's a couple different types of resistors. Usually they look like these. These are little carbon resistors. You might even see one that looks like this. This is known as a ceramic core resistor. Okay, here's where I'm going to finish my lesson here. On Monday, we're going to do an activity where we're going to make some circuits. And I want to show you how that looks today. And I think I'm going to have to go sit at my computer to do this. So even though I'm not at the back of the room, make sure you pay attention here still. We're going to use an online simulator to do this. Okay. Guys, I know I'm not at the back of the room. Stay with me here, okay? Rather than me give you wires and light bulbs and batteries, I found a simulator online that I think works really well. And so this is going to be our assignment. We're going to do an activity called building circuits. And this is what we're going to do Monday in the computer lab. I'm going to take you guys to this website right here. So all you're going to have to do is just click on the link here. And this is a virtual construction lab. And the reason why I like to do a virtual lab is because we can accomplish a whole lot more in an hour than we can if I have to give you like physical wire. It takes a long time to do it, like for real. But this is kind of fun to play with. I want to show you an experiment kind of on how this looks. You turn on the simulator and you'll click on the lab itself. And then you get a chance to kind of make some circuits. So I'm going to move this out of the way. And basically, you guys are going to get a chance to experiment. Like, take over here a wire and drag a wire out. And then maybe drag out a battery and drag out another wire. And you can actually bend them around a little bit if you need to. And then you can bring out a light bulb, bring out a wire. And if I connect this, it turns on, yay! Which is kind of cool. But there's more things we can do. For example, you can take this battery right here. And currently, this is a 9-volt battery. But there's a little slider on the bottom. I can make the voltage go up. Now, look at the electrons here. See how slow the electrons are going right now? But if I were to take the voltage and increase the voltage, it's actually getting pretty bright. It's actually possible on the simulator to actually cause certain things to start a fire because you actually have these electrons running through here so fast that there's actually no resistance. So it's actually possible for you to then like turn this off and put on, say, like a resistor. And so now when you put the resistor on, I can then take this and I can increase the resistance. As the resistance goes up, the light bulb goes down. There's other fun things you can add on. You can add on things like a bigger battery. So I can put a second battery into this. And now we've got problems. Because see how fast these electrons are running through here? So fast so that it's actually causing us a bit of an electrical problem. So maybe what we need to do is we need to up our resistance here. And that still apparently isn't enough. Maybe I need to, okay, look at this. This is 10,000 volts. Yeah, maybe 10,000 volts is a bit too much. Maybe 500 volts is a bit better. Or I could turn it all the way to 100,000 volts, and you can see why this is causing problems. Okay. Now, one of the other things you can do is you can make your circuits look like this. I'm going to turn the circuit off for a bit here because it's on fire. One of the other things you can do though is you can change from it looking like a kind of a real circuit here. If you toggle this little switch down here, it'll actually turn it into the other conventional symbols. Like, look, see how here's the battery symbol now? Here's the battery symbol here. Here is the resistor symbol, and here's the light bulb symbol. So all you got to do is just toggle the switch and play with that. So the last thing I want to do today is then talk to you guys about the two different types of circuits that you can make. And on Monday, basically I'm going to give you guys a day to play and try to build circuits. And I think the first thing most kids want to do is they want to build like the biggest one they can and light things on fire. And by all means, you can take a few minutes to try that. I'm going to give you a few tasks to build as well. So one of the things I'm going to ask you to do is to try to build a circuit that looks kind of like this, where there's going to be a battery, there's going to be an ammeter to measure current, there's going to be a 10 ohm light bulb and a 10 ohm resistor, and we're just going to do some tests and build circuits and see how they work. Okay. But the last thing I got to cover before I get there then, so I need to go back to my notes here, is the two types of circuits. So this is my last topic, series and parallel. And this is the perfect time of year to talk about this because it's Christmas time and maybe you've had to go put Christmas lights somewhere. And you put out a Christmas light and some of the strings of lights are all of a sudden turned off. And like you ever have this before where like one light gets burnt out and it screws up the whole series? Yeah. That's what I want to explain here. They're known as series and parallel circuits. If you have a series circuit, here's how it looks. You have electrons running through this battery right here, and they're going to go through all 3 light bulbs in a row. And this is a series circuit right here. And here's the problem though. Let's say that this light bulb here is working. Let's say that this light bulb here is working. But let's say that this light bulb right here, let's say that it gets burnt out for some reason. Well, if this light bulb here gets burnt out, the electrons can try to go from here to here, from here to here, from here to here, but they get stuck right here. And if you ever have a series pathway, if one light bulb gets burnt out, the whole thing stops, which is super frustrating when you're trying to put out Christmas lights. The other way you can do them is what's known as a parallel circuit, where there's really 3 different routes or routes that electrons can take. Let me show them to you. You can have electrons go through this route right here in black, or you can have electrons go through the middle route right here in blue, or you can have electrons in green go through the final route right here in green. And hypothetically, let's say that one of the light bulbs now burns out. Let's say that this light bulb right here now burns out. Well, okay, this one's burnt out, but the other 2 pathways, they're still connected. And so it's actually very nice sometimes to try to put things in the parallel circuits because of the fact that if one goes, the rest still work. However, there's a downside. It requires more work and more wiring, but if one fails, the rest still work. So my last slides are a couple of pictures, and then I'm going to be done with my lesson. Here's a picture of a basic single circuit. You guys can see that we've got a battery right here. We've got a light bulb over here, and this is a device measuring amps. And I want to just refer to this. Right now, we have 2.5 amps. What is amps again? What does amps measure? Which is how many electrons are moving, right? So there's 2.5 amps of electrons moving every second, basically. But here's our next picture. Now I put 2 light bulbs on. Are these light bulbs in parallel or in series? Series, yeah, they're both in a row. And what did you notice? They used to be this bright, and now they're this bright. What happened? They have to share those electrons, yeah. Some of the electrons right here have to get used to make electricity, and so do some of them right here. And you'll notice that the amps right now has got cut in half. Right? There's not as much amps running through this thing, and so both light bulbs are now dimmer. This is one of the downsides to maybe doing a lazy job at building something in series. The other problem is if this light bulb here burns out, they both die. This is now what parallel looks like, and you'll notice that if I were to measure the amps, it's actually back up to 2.5 for both, because what happens is these electrons can either go through loop 1 or they can go through loop 2, but the electrons aren't getting slowed down doubly. Okay? Like the electrons that choose to go this way, they only have to run through one device. the electrons that choose to go this way, they only have to run through one device. And so they can still run at 2.5 amps. But if I go back to the previous picture, the electrons that go through here, they have to run through device 1, and those same electrons have to run through device 2, which means they're getting slowed down, right? There's not as many of them. So that's what we're going to explore basically in the next couple of days, is the idea of parallel and series circuits. Okay. So let me do one last thing here, and then I'm going to give you guys some free time to go work. I want to show you your next assignment, okay? Because there are 2 this unit. So we ideally have already done number 1. There's assignment number 2 now. Let's talk through a couple of questions because many of them you can answer. We have now finished almost all of the unit. So I'd love to chat with you guys for a few minutes about these questions, then I'm going to give you free time. So just read along with me here. Question 1. Do you guys think you could articulate now, why is it unsafe to remove that 3rd prong of electrical plug? Because what's the point of it? It's a ground wire. It's to try to keep you safe. Right? Okay. And here's another question that's really on stuff we've talked about before. Can you articulate to me the differences between static electricity and electrical current? But now I want to show you some of our new questions, ones I want you to work on today. Like this one here, strings of Christmas lights, which look like these guys right here. Sometimes what happens if one bulb burns out, the whole string of lights goes out. Can you now explain to me why this occurs and how we try to fix this problem? Yeah, so rather than making them go in series, we try to make them go in parallel. And then here's the last question I want you guys to be able to do today, but you can probably go past that. I want for you to draw me a circuit with a lamp, a cell, and a switch. And what I mean by that is I want you to not draw it looking like this, though. I want you to draw it using these symbols here. So I mean, more or less, this right here is the one you'd need. An electrical source, a switch, and some sort of load. Okay. So don't draw me like a real looking one. I want you to practice using these symbols here. This is my goal for you guys today. I want to like break it up into little pieces. I would like for you guys, to the best of your abilities, to try to finish questions 1 to 4. I'm not asking for a lot, because really all of these are things that we can do. And if you guys can go past question 4, that would be fantastic. Because really, I don't want you guys to procrastinate. We've only got 23 days left. So if you're going to be like, yeah, I'll get to it, well, like, it's going to get caught up with you. So does that make sense for today? Tomorrow is also a work day, but tomorrow I want to suggest we work on other things, okay? So I'll turn off my recording, and you guys are free to work somewhere else in the building if you'd like. But that's my goal for you. Finish questions 1 to 4 on this assignment for tomorrow. Sound good?